My name's Peter Evans, this is Paul Vagin and Mika Costas, and Bruno is currently operating the camera. We've come over from Holland and we're here to look at recent Rotliegend desert analogues in the Tunisian dune field. Here we're standing at the margin of the Sahara Desert, and we're here specifically at the moment to look at different types of desert processes on these Aeolian dune forms. Looking at the following deposits and their associations: Aeolian dune sandstones, interdune Sabkha silty sandstones, lacustrine Sabkha mudstones and salt, and streamflood sandstones and abandonment mudstones. Okay, we're standing here on what's really got to be described as a modified barchanoid dune, and we'll be looking at a process called sand flow bedding, which is basically the avalanching of sand down the slip face of a sand dune. So I'm going to walk over here, and you can see that the angle of repose here is around about the 30 degrees to 34 degrees mark. It's fairly unstable, and what happens is the sand either avalanches down and causes a slip face apron called a sand flow bedding, or the grains saltate over the crest of the Barkhan dune, get to the crest and fall as dust, as fine dust. And you can see here that when I'm throwing it, the finer material lands second and the coarser material lands first. That's normal grading. You get very fine laminations of fine and coarser material. They're quite nicely sorted, each lamination, but in combined together they're actually fairly bimodally sorted. However, look at this. When I create a sand flow bedding, which is basically by the avalanching down a slip face, and you can see here on the unstable slip face slope, you're getting avalanching, forming an apron of sand slipping down the slip face, and actually the bedding is inverse graded. It's actually throwing up the coarser grains up to the top, and you're getting inverse graded bedding. Now at this angle, which is around about the 32-34 degrees mark, with the inverse grading as well, this is actually very diagnostic criteria for actually recognising Aeolian dunes and the environmental deposition from the subsurface, i.e. core material. These sinuous crested barchanoid dune forms have had their slip faces modified by reversing wind directions. Bifurcate asymmetrical wind ripples migrate over the dune forms. Crescent-shaped Barkhan dunes coalesce into sinuous crested barchanoid dunes and then more straight-crested transverse dunes. Here is an example of a major sinuous crested transverse dune form with a 15-metre high dune slip face. Here we're standing in the middle of an interdune Sabkha area. Over towards my left you can see a marginal dune field with small barchanoid dunes. They've also got some vegetation on the top of them. But coming in here you can see a seaway, which is basically where a lacustrine has transgressed over this area, and then further round to the right you can see also where it's slightly transgressed up the margin of a small dune field here to the right. Area would have been transgressed with a very shallow depth of water, and it probably was only a few inches in depth, and then it evaporated away, and the salts have been reprecipitated out after it was evaporated away as a gypsum. It's this gypsiferous crust. It's very crusty, very dry. And beneath it we have sand, which is it's gypsiferous sand from the surrounding dune fields, which is blown in here. Note also that we've got this grey and white area here, which is actually where it was dampest latest, and that's actually where we've got a little bit of halite being precipitated out as well. So it's mainly gypsum with a little bit of halite. So now we'll go over and we'll take a look at a trenched section in this interdune Sabkha deposit. Here you can see it's predominantly this brown, very fine to fine-grained sandstone with some siltstone laminations. It's wavy bedded and possibly adhesion rippled. It's also got some mudstone down here in the bottom, which is this brown lamination. And we've got some gypsiferous patches here as well. Later on, when these are buried, this gypsum, which is really calcium sulfate with 2H2O added onto the end, hydrous, it dehydrates into anhydrite and forms anhydrite nodules. And here you can see also on the top we've got this dry gypsiferous crust as well. Now we're standing on the edge of an interdune Sabkha area. Actually, this is quite salty, this area. You can see the salt shimmer, the grey area on top here. And also, if we look down closely here, you can see some evaporitic adhesion wart features caused by the saline water table rising and then the salt crystallizing out on the top, forming this wart-like structure. In between these warts, it got slightly more saline, and actually salts precipitated around as this grey sheen. Okay, we're standing here on the interdune Sabkha. It's midday. The temperature's got up to around about 35 degrees centigrade. Of course, it's early October. It is quite hot actually. It's very dry heat though, but we're persevering all the same. Here you can see the interdune Sabkha area over towards the left. It's quite laterally extensive. It's dried out on its surface with gypsum. It's got a gypsum crust. But this location shows the proximity of the water table in the fact that actually the water table here comes to the surface, as you can see in this ponded area here. It's very shallow water, only about 1/2 metre in depth, and it's also quite sweet water as well. The water's actually got very little sodium chloride in, although it's probably got a high calcium sulfate content. There's also reeds growing on the edge of the lake as well. Eventually, this pond will be desiccated and evaporated away until actually the surface is completely dry. This will therefore represent one of the Stokes bounding surfaces or deflation surfaces that we refer to as being all important in this area. These deflation events represent timelines in the area, in the fact that they're laterally extensive and actually they can be correlatable in the subsurface. Of course, when we get a dune field migrating over and then the rise in the water table, truncation of these dunes down to this water table level, then of course we get the next facies on top, the dune sandstones. So you can see over there in the far distance, you can imagine if those dunes actually migrated over here onto this laterally extensive first order bounding surface, of course you'd get this interdune Sabkha and Aeolian dune cyclicity. Here on the side of the Chott El Djerid desert lake, you can see over towards my right we've got a shadow dune behind some vegetation here. The wind's been blowing from my right to my left, and here we have a small ponded area where some silty mudstone has been deposited. It's now desiccated, and you can see close up it consists of curled and cracked mud flakes which have been slightly desiccated away. So we're now going to move further into the main lacustrine belt, and there we hope to see also some halite.
That's old Kebili coming up.
We are now standing on the margin of the Chott El Djerid desert lake, where we encounter some curious geological features. We can see remnants of early cemented gypsum dunes which stand as outliers in the desert lake. We are interpreting these features as having formed during annual flooding of the desert lake and erosion by wave activity of an older neighbouring gypsum dune field. These gypsum aeolian dunes show very well developed grainfall and sandflow cross-bedding. These sands also have vertical gypsum cemented fractures. These features probably also formed due to a base level change in the southern lake margin where we now stand. A dune field beach cliff is now developed with stacks or outliers of cross-bedded dune sands standing proud in the desert lake. We are now passing northwards from the main dune field via a series of sheet dunes and shadow dunes from a sandy interdune sabkha to a more silty and gypsiferous lacustrine sabkha area. You can also see the grey sheen on the darker lacustrine sabkha surface, which is salt precipitation. From the edge of the desert lake, more into the centre of the desert lake, you can see here we've got a lacustrine sabkha which is very laterally extensive. It's almost horizontal. On the surface it's also got these adhesion wart features. These adhesion wart features consist of gypsiferous sand surrounding halitic crusts. Now these halitic crusts grow towards the wind, which in this case is towards our right. They form these evaporitic adhesion wart features. Now zooming in here towards a trenched section, you can see it consists of 3 cycles. The first cycle is horizontally laminated embedded gypsum. This gypsum is probably both wind blown gypsum and also normal in situ evaporitic gypsum. And then we pass up here into this black bituminous algal material, and this probably was deposited during a still stagnant ponded time, when the pond actually dried out and formed this black bituminous material. The next desert lake transgression passed over it, and we had deposition of both wind-blown detrital gypsum, and also we've probably got some in situ evaporitic gypsum. And then we passed to the third cycle, which truncates it here, and you can see a little black bituminous material from the previous cycle, and then we pass up into gypsum with a hard halitic crust. And of course I've already described these are these halitic cubic minerals which actually grow towards the wind in this direction, and these are actually contorting the underlying gypsum, which you can also see here. Moving further over into the centre of the desert lake, we get accumulation of bedded halite, which is formed by the evaporation of saline waters, forming these characteristic polygonally cracked halite crusts. During desiccation of the desert lake, as the salt concentration increases towards the desert lake centre, the least soluble salts precipitate out first, such as limestone and dolomite. Then the less soluble salts will precipitate, such as gypsum and anhydrite, and finally halite you can see here, and potassium magnesium salts such as carnallite. These are the so-called squeezing salts of high mobility and high solubility, which crystallize out last. At the edge of the desert lake we encounter the beveled remnants of a previously deposited aeolian dune. The curved arcuate morphology preserved on this Stokes deflation surface is the preserved toe sets of an early cemented dune form, and represents a timeline and a first order bounding surface. These first order Stokes deflation surfaces form after the following: 1. Deposition of aeolian dune sand, 2. Desert lake transgression, after which 3. interdune sabkha silty sands are deposited, after which 4. Further lake transgression occurs, and then finally 5. Major desiccation after the desert lake transgression. Deflation and truncation then occurs down to the water table of previously deposited lacustrine, interdune and aeolian dune deposits. This forms a laterally extensive timeline or Stokes surface which can be correlated over thousands of metres. To the north of the study area, the Atlas Minor Mountains act as a source for streamflood deposits which form alluvial fans. These fans pass down into major streamflood watercourses, or wadis, which transport water-laden sand during ephemeral flash flood events into the main desert lake basin. Here we see a dried out watercourse passing down into the basin. We'll now take a closer look at some streamflood deposits passing down from the source area, which is the Atlas Minor Mountains. We'll also look at a streamflood course which passes into a small desert lake to the northwest of the field study area. Coming out of the mountains, we can see the streamflood channels which form a braided outwash plain on the relatively flat-lying, dried-out desert lake. Sand accumulates on low-relief point bars formed during flooding and channel switching. Mud cracks form associated with desiccation of mud which was deposited from suspension after the rapid waning of current activity and after floodwater discharge lessened. On the far side of the stream is a parallel and trough cross-bedded sandy fluvial point bar with an active erosive cut bank. Note the shape and lateral extent of the abandonment mudstone deposits, approximately 10 metres by over 100 metres, and these probably represent non-correlatable shales in the subsurface. On the edge of the desert lake, close to the mountain belt, is a well which indicates the presence of a piezostatic head, since it is blowing out fresh water. This concludes our presentation of the Tunisian desert sediments. We have seen the following facies and their associations: Aeolian dune sandstones, interdune sabkha siltstones, lacustrine sabkha gypsiferous mudstones and salt, streamflood sandstones, abandonment mudstones, and of course we've had a look at the source area for these deposits as well.